So let's read through this problem together. Welcome back to another lecture of fluid mechanics. So an incompressible fluid is being squeezed outward between two large circular disks by the uniform downward motion of the upper disk moving at velocity v0. Assume one-dimensional radial outflow, derive an expression for the radial flow at any given radius vr. So this is another control volume problem. And let's again review the type of equation that we will be using to solve this equation. It constitutes mass conservation because if we define our control volume wisely, the mass flowing out of mm, the 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 volume change or the volume decrease by pressing the two large circular disks together. Um, the volume change in the disk should equal the volume uh, flow out of the control volume. Because as we see, if we press these two disks together and we define a control volume, so if we define a control volume to be like this, when you press the two plates together, the control volume will get smaller. Uh, yes, the control volume will get smaller in volume because the height is decreasing. So the volume of the control volume will decrease like this. And we can take the control volume area to be defined by the radius r. And as the upper circular disk moves down, the volume of fluid in this control area will decrease. But that decrease in fluid must result in an increase somewhere else because of conservation of volume. The lost volume leaves radially through the cylindrical surface of the control volume of radius r. The radial velocity at radius r is vr and the height of the gap is ht. The flux through this control volume will be calculated. So basically, we're taking our control volume to be defined by this radius r. They give us this hint, wonderful. And although the r will stay constant as the plate moves down, the height decreases, resulting in a decrease in volume that is subsequently manifested as this volume flow outwards. And that's what conservation of mass is. And since over here, the liquid is incompressible, conservation of mass is equal to um, conservation of volume applies over here. And conservation of volume translates to conservation of mass. Um, so yes, and over here we chose a deformable control volume. Because it is able to deform when the plates move down, the control volume height decreases. Yes. So what are the key equations that we'll be using? Again, we saw this equation just previously, but it is essentially this equation over here, the conservation of mass equation that we will be using. Let's write that equation here more explicitly. So, d dt of the control volume rho dv plus integral of the control surface times the rho times the relative velocity dot dA is equal to 0. So over here, we have to find what each of these integrals constitutes. First, we'll find what the expression for this integral translates to. Let me see if I can, yes, oops. Move it downwards. All right. So what this is saying is basically is the rate of mass flow out of the control volume. And that is equal in magnitude to how fast the volume is changing. So the plate moves down at a rate of VO, and the radius stays constant. So the the volume of the control surface cylinder can be represented as pi r squared. So pi r squared from this area below here times height, which is ht, so times h. Except h is varying with time, which makes it applicable to be an integral. So yes, and so this will give us d dt of rho times dv, and dv is already taken care of by this differential volume, by this volume over here, the volume of the control volume, which is pi r squared h. So d dt times rho of pi r squared h. Yes. And differentiating this will give us rho pi r squared dh dt. And r is taken to be a constant here. And now what about for the control surface? For the control surface, we want to find the value of this integral over here. Let me select all of it. Yeah. And the value of this integral is going to be equal to the the rate of flow of the fluid out of the control volume surface, dot the normal vector of the surface area of the control volume surface. And basically, do they point in the same direction? Yes, because we have a cylinder, and on a cylinder, the surface area of the cylinder is this portion over here. And this is an area that is oriented with vector pointing outwards, directly outwards. So over here is pointing outwards, over here is pointing outwards. And the outflow velocity vector, which is VR, is pointing exactly in the same direction as the area. So consequently, VR constitutes the U relative we see over here, and A constitutes the dA that we see over here. So U relative dot dA um, is going to be equal to U relative A cosine theta, and theta is the angle between these two vectors, which is 0. So cosine of 0 is 1, so this is equal to U relative times A. And it is positive because the vectors are pointing in the same direction. So yeah, that's pretty cool. And yeah, so this means that this will be equal to P times VR, which we will represent as V. And what is the surface area of the cylinder? The surface area of the cylinder is, we can unwrap it as such. Think about peeling it away. So we can unwrap it to look something like a sheet that has length 2 pi r and the height of h in this case. So our area is going to be 2 pi r h. And yeah. So we have these two crucial informations. So now we have to combine them in this equation. We simply add these two values to get rho pi r squared dh over dt plus rho v 2 pi r times h is equal to 0. So solving for v, which is the radial flow at any given radius, we have that basically v is equal to rho or negative rho pi r squared dh or dt over rho times 2 pi rh. Certain things cancel out. The rho cancel out, the pi cancels out, the r cancel out to remain with 1r, and we are left with negative r over h dh dt. And sorry, don't forget this 2 over here. Yes, so it's going to be negative r over 2h times dh dt. So what is dh dt, you might ask? dh dt is the change in height with respect to time, and it's given by um, negative v naught. So negative v naught. Yes. And because that is the rate at which the upper disk is moving downwards. So we can simply substitute negative v naught for dh over dt, and we get negative r over 2h, or actually it's positive now because we have two negative signs times v naught. And this indeed matches our form over here. So we know that it is correct. Thank you guys so much for watching this video. I hope it was helpful for you guys in getting a better understanding and proficiency of control volumes. And we will see you next time. Here's a quick recap of the problem. I'll be posting these slides afterwards, and see you next time.